So today I wanted to talk about a misconception I had about Gibbs phase rule, but then I realized that maybe I should properly introduce what a Gibbs phase rule is so that I can actually talk about the misconception which I had. So I divided this concept into two videos. So in the first video, I would basically derive and explain what's Gibbs phase rule, and in the second video, I would talk about what was the misconception that I had. So yeah, let's jump into the video. Let's say you are aluminum, but you are not alone. There are other aluminum atoms like you. And all these aluminum atoms come together and they sit at certain distances in a certain pattern to form something called a phase. This, for example, is one phase. Now, let's say there is a copper atom which would like to come into your phase. So since you are nice, you would accommodate copper atom by removing one aluminum atom because we just want to maintain 100% composition ratios. So now out of the 36 atoms, one atom is copper, the rest are aluminum. And you didn't really have to change your structure much, you just had to accommodate copper. Now more copper starts coming in, and since you're happy, you can still accommodate more copper. As this happens, more and more copper starts coming in. But let's say now the copper amount is exceeding, and you, as a phase, are becoming somewhat irritable or somewhat irritated. So you say, okay, let's do something. The next coppers which are coming, you form a phase which is slightly different from your aluminum phase because they have a different structure, maybe different distances. So basically, this is now another phase, and there is no problem between this aluminum phase and this copper rich phase. So basically, you both are happy to share the space, and even this copper rich phase can still accommodate some aluminum. So the extra copper which got into the system actually formed another phase because after some point you in the aluminum phase you were not really happy with too much copper, so you said yeah, form a different phase. So this was one way that you could actually change the phase. Now there was not just one phase but now two phases. But is there something else which can also change phase? For example, temperature. You know that if I just take pure aluminum, it's a solid at room temperature, but if you heat it, you can melt it and it becomes a liquid. So that's a different phase. Perhaps you can also change it by applying pressure to the phase. So the question becomes, or the actual question is, how many degrees of freedom or how much freedom do I have in terms of, let's say, temperature or in the composition before I have to form another phase? So this is the question we are trying to answer, or we are trying to find out how much freedom do I have before I have to step into something else or before I have to cross a phase boundary. But why should we really care about this? Let's take an example, which is foil to flight. Both materials are made of aluminum. Here, the aeroplane body is made from aluminum alloy. However, they both serve two different purposes. Aluminum foil, probably you use it to make biryani, whereas flights we use to fly, right? But the key difference is that aluminum foil is majorly pure aluminum, whereas in this aeroplane body you have some other alloying elements like copper, zinc, magnesium, which allows to form other strengthening phases inside aluminum so that it is actually strong enough to actually fly. So it becomes really obvious that we need to understand the freedom a phase has before it has to change into another phase or cross a phase boundary. So in order to do that, let's take a simple phase. We call it alpha. And first we need to define its stability by a function. And we do so in thermodynamics, at least in some conditions, using a function called Gibbs free energy, which is denoted by G. Now G is sort of like the mood of the phase. That is, it represents its stability. So if you think if alpha phase is unhappy, it means that it is unstable. If it is at equilibrium, it basically means that the alpha phase is at a bliss-like state. So this function is really important because it defines the stability of the phase, and that is what we are trying to look at. Now we have to figure out what are the variables which we have, and in general cases the variables which we have are the temperature and pressure, like we saw before, and the amount of components that we have. So important thing to look at is how the G is sensitive to a change in temperature, and that we mathematically represent like this: a change in G with respect to a change in temperature. But since we want to look at the change in G with only with the change in temperature, we have to maintain the other things constant, and that we usually represent like this. Instead of D, we use a dou. And one way to think about it is like this, that this is the potential of temperature to change G. Similarly, a pressure will have certain potential to change G, and also the components or the amount of components will have a certain potential to change G. But if you remember, as I said before, the amount of components, that is all of them, they should add up to 1. That is, at one case, you can only simultaneously change copper and zinc, because aluminum amount would be fixed based on the amount of copper and zinc you have. Similarly, if you change aluminum and copper simultaneously, the amount of zinc is fixed because all of them should add up to 1. So you had two variables from temperature, pressure. The number of components were 3, but the actual variables are just 2 because the third component's amount is fixed by the first 2. So basically you have, in this case, variables which is C minus 1, that is 3 minus 1, and then two broader variables which are temperature and pressure. So you have 4 variables in this case. Now let's say there is another phase in the system. We call that beta, and it is primarily composed of copper with some aluminum and zinc. Now for this, again, you have these two broader variables which are temperature and pressure. But with respect to components, you have only C minus 1. So for two phases now, you have 2 times C minus 1 plus 2, that is 2 times 3 minus 1 plus 2. So total of 6 variables for 2 phases. And let's say you had P number of phases. In that case, the number of variables would be P times C minus 1 plus 2. So we figured out how many variables we have. Let's say if there was no physics, in that case there was no equations governing the phase's stability, then we basically have the number of freedom would be equal to the number of variables we have, that we can change all of them. But it so happens that the physics governs the phase's stability. So we need to figure out what are these equations which are governing the stability of a phase. In order to do that, let's say what it actually means to be at equilibrium. Let's take 2 phases, alpha and beta, which are composed of one aluminum copper, the other one copper and aluminum. And let's say these two are at equilibrium, that is, they are at peace, they are at a perfect state of bliss, they are happy with each other. In that case, what it means physically or mathematically in this case is that the potential for aluminum to change the Gibbs free energy of alpha phase is the same as potential for aluminum to change the Gibbs free energy of beta phase. That is, if aluminum sees that it has the same potential in both phases, then it doesn't really care where it is. So this is the equation which is telling you that this to be in equilibrium aluminum, the potential of aluminum to change Gibbs free energy should be same in both of the phases. And this basically is also called chemical potential. And since there is also another component, the potential for copper should also be same along the 2 phases. Now let's say there is another component called zinc in both of them, then you basically get another equation, which is potential of zinc should be same in beta as well. So these are 3 equations for 3 components, and basically for each phase you have basically one equation. Let's say there was another phase, gamma, which is also at equilibrium with alpha and beta, then in that case you have an additional equation saying that the potential of aluminum is also same in gamma phase as well. So if you had 3 phases, you have 2 equations, and for each component you have one set of equations. So basically you have for each component you have p minus 1 equations. So the number of equations, let's say if you had c components, you would have c times p minus 1 equations. So we figured out how many variables we have and how many equations we have. So now my degrees of freedom, or the freedom which I have, would be how many variables I can change according to my wish without any restraint. Whereas the equations are telling us that these variables cannot be changed according to your wish, and they are actually interlinked with each other because they are governing equilibrium. So if I were to figure out how many freedom or how many degrees of freedom I have, I would just have to take the number of variables I have and how many equations are there and subtract them. And the remainder would be the degrees of freedom. Another way of thinking about this is that if we had 3 variables and there are 3 equations, then in that case, I basically know all 3 variables by solving the 3 equations. So degrees of freedom are 0 because I cannot change one variable according to my wish. So if we do this, use this expression and subtract the number of variables and the equations, we are left with degrees of freedom. And this gives us our popular expression, which is Gibbs phase rule. P plus F is equals to C plus 2. I hope I was able to explain the Gibbs phase rule in this video, and in next video I will try to explain the misconception I had while applying the Gibbs phase rule to a phase diagram. Thank you for watching.